Hello, everyone. Hello, Dallas. Everyone else dialed in from all over the world. Good morning, good afternoon, good evening. Welcome to Angelbeat's Physical AI and Robotics event. For those who started your morning coffee, hopefully you added some tokens in it and ready to produce some intelligence. My name is Karthik Amartrajan. I'm one of the physical AI leaders here in NVIDIA. I'm sorry I couldn't be there in person. I had to attend a conference in Germany, but super excited about the event. You should be as well and as energized as you can because we're going to talk all about physical AI, machines that think, robots that act. And to do justice to a physical AI keynote in 30 minutes is probably, not good enough. But we're going to try our best, right? And basically tease yourself into the concept of robots and world foundation models and recipes to post train and fine tune and adapt in the physical world and take away something from here. If there's one thing I'd like you to take away from this keynote is that one day everything that moves will be autonomous. And that's like paramount, and that's not going to change. And so, to set the theme, let's start watching a video to inspire yourself, get you guys energized, get your juices flowing in, and so you can get the most out of this event. And hopefully, you can hear the audio in it. I'm positive I've shared this. And with Jensen's voice in the background, it's only going to get even more energizing. So, here we go.
The era of robotics has arrived. One day, everything that moves will be autonomous. Researchers and companies around the world are developing robots powered by physical AI. Physical AIs are models that can understand instructions and autonomously perform complex tasks in the real world. Multimodal LLMs are breakthroughs that enable robots to learn, perceive, and understand the world around them and plan how they'll act. And from human demonstrations, robots can now learn the skills required to interact with the world using gross and fine motor skills. One of the integral technologies for advancing robotics is reinforcement learning. Just as LLMs need RLHF, or reinforcement learning from human feedback, to learn particular skills, generative physical AI can learn skills using reinforcement learning from physics feedback in a simulated world. These simulation environments are where robots learn to make decisions by performing actions in a virtual world that obeys the laws of physics. In these robot gyms, a robot can learn to perform complex and dynamic tasks safely and quickly, refining their skills through millions of acts of trial and error. We built NVIDIA Omniverse as the operating system where physical AIs can be created. Omniverse is a development platform for virtual world simulation, combining real-time, physically based rendering, physics simulation, and generative AI technologies. In Omniverse, robots can learn how to be robots. They learn how to autonomously manipulate objects with precision, such as grasping and handling objects, or navigate environments autonomously, finding optimal paths while avoiding obstacles and hazards. Learning in Omniverse minimizes the sim-to-real gap and maximizes the transfer of learned behavior. Building robots with generative physical AI requires 3 computers: NVIDIA AI supercomputers to train the models, NVIDIA Jetson Orin and next-generation Jetson Thor robotics supercomputer to run the models, and NVIDIA Omniverse, where robots can learn and refine their skills in simulated worlds. We build the platforms, acceleration libraries, and AI models needed by developers and companies, and allow them to use any or all of the stacks that suit them best. The next wave of AI is here. Robotics, powered by physical AI, will revolutionize industries.
All right. So hopefully that was inspiring enough. and sets the right tone for the keynote, right? And so, what is physical AI? And look, from an NVIDIA perspective, this is $100 trillion industry. If that doesn't excite you, and if you don't want a slice of that 100 trillion, you must be joking. So this is a massive industry that's about to unlock here, and we are at this pivotal juncture and time, and it's a once in a lifetime opportunity. And so, how do we get here? Automating tens of millions of factories, hundreds and thousands of warehouses, with video being an important sensor, with 2 billion cameras worldwide. That's an important piece of sensor. Humanoids are exciting. There's going to be a billion humanoids pretty soon here. But also think about tens and thousands of autonomous mobile robots, or AMRs and AGVs, which are also important. And they are producing about 1.5 billion cars and trucks, soon to become 2 billion. And all of those 2 billion cars and trucks will be autonomous. Again, everything that moves or monitors that moves is going to become autonomous. And with that physical AI segue, let's start defining what it is. Physical AI are models that perceive, learn, reason, and act in the physical world. So these models are grounded in the laws of physics. They can take in image tokens and text tokens as input sensors, and then produce what's called action tokens. And then physical AI will embody essentially multiple types of robot embodiments. So we have factory robots or facility robots. We're taking in camera capabilities and turning these facilities into robots themselves. Then we have robots, which are the humanoids, the AMRs, the AGVs, the autonomous forklifts. Then we have autonomous vehicles. And then recently, we are even turning external open spaces like cities into robots. So you have all these robot embodiments coming into physical AI, and it's just getting really, really exciting. Just to set the segue in terms of what NVIDIA is, I mean, of course, everybody knows about NVIDIA, but it's important to understand that we are an AI infrastructure company. It's not about the fact that we just make GPUs and compute is just one piece to the puzzle, right? And so if you think about this 5-layer AI cake, NVIDIA operates in all these 5 layers, from energy to chips to infrastructure to models to applications. And so on top of these 1 gigawatt AI factories, those that produce these tokens to run physical AI and bring it to scale, you have NVIDIA Blackwell and Vera Rubin GPUs that are powering these factories. And on top of these, we have these open community models, our own models, as well as other open source models, physical AI models, models that are grounded in physics, LLMs, VLMs, and so on and so forth. And then on top of these models, you have these applications, and we have accelerated software stacks and software platforms to drive some of these models and applications and deploy them in the industrial AI space, anywhere from all physical spaces from edge to the cloud. So again, we operate across all 5 layers of the AI cake, and to maintain autonomy over these 5 layers is really a difficult thing, and we are super proud of the fact that we do so. And so a little segue into scaling loss. It'll be a remiss to not talk about what's happening in the market right now with these new scaling laws. As you move from perception AI to the chat GPT moment of generative AI, of course, agentic AI has arrived, and there's world of agents, and physical AI is in our doorsteps already. And just shortly, a little ago, there were these 3 scaling laws. Pre-training scaling, which is taking a model that's trained on enormous amount of internet data. Post-training, which is taking the models, adapting, and making sure they learn to reason using techniques like fine-tuning and reinforcement learning. Pre-training is generally trained on internet. Post-training is adapted to target scenarios. And then came inference or test time scaling or long thinking. In other words, inference ended up producing really good results because of this long thinking and reasoning. Arrival of DeepSeek changed the world with respect to reasoning. And that just changed the inference game big time. And that's creating a massive number of compute tokens, right? There's the mixture of expert models running on our infrastructure like NVL72 and so on and so forth. But the biggest change that we're seeing now is this fourth new scaling law. We saw this at GTC San Jose, if you were there at the event, where AI is starting to talking to AI, and this is called agentic scaling, and this is a big, big deal. So you're looking at agents operating in the world of both text-based scenarios, physical AI-based scenarios, and suddenly text-based agents are talking to physical AI-based agents, and it's changing the game of thinking, listening, reasoning, and so on and so forth. So imagine there's a vision language model, and it's creating an output to generate a task to a vision language action model that is affecting a change inside a work cell of a robot. And imagine that you're missing a particular part, and that is talking to another agent to order a part in an ERP, and before you know, the part is ordered. That's an example of agentic scaling or AI talking to AI, and we are in that era and space. And this is like a big, big game changer. So talking about evolution of AI agents, what's happened in the market is the industry is clearly moving from foundational LLMs and single or simple multi-turn prompts. We're entering into a phase where reasoning enables agents to reflect on their own processes to deliver significant outcomes. And this evolution is marked by two major scaling milestones: the shift from basic chat to reasoning capable systems that use reflection to improve accuracy, and the transition to self-evolving agents thanks to OpenClaw, a once in a lifetime internet or even larger than an internet moment that we saw in January 2026. This notion of long running agents or self evolving agents that's going to operate autonomously and execute things on your behalf has been a massive changer. And the numbers you're seeing at the bottom, just as we were thinking about test time scaling and reasoning with DeepSeek, the compute was at 100x. Now we've reached 1000x with respect to self-evolving agents, and this is inevitable, guys. And so the ChatGPT moment for autonomous agents has clearly arrived. March 2026, OpenClaw repositories surpassed historical star counts, beating both the Linux kernel and React in terms of the most starred software project in GitHub history. And that's a big, big deal. And so given what it surpassed and all the popularity it sort of gained, it is clearly being noticed. And so to make sure that we celebrate this historical OpenClaw moment, we wanted to onboard OpenClaw, recognize the fact the world of long-running agents has arrived. And we also announced something called NemoClaw that we'll talk about. But let's take about all this fun moment around long-running agents and OpenClaw.
An open source project just dropped.
Andre Karpathy has just launched something called Research is a huge deal.
You give an AI agent a task, go to sleep, it runs 100 experiments overnight, keeping what works and killing what doesn't.
I really love what my stuff enables that person to do. And we had like one guy, he told me like he installed it at his 60-year-old dad, and like they made beer, connected the machine via Bluetooth to OpenClaw. And then we automated everything, including the whole website for people to order.
Lobsterlager fertig sein.
Everyone is talking about OpenClaw.
We want to build OpenClaw with OpenClaw.
What is OpenClaw?
Hundreds of people are queuing up for lobsters in Shenzhen.
Believe it or not, there's already a claw con.
All right. So hopefully the claw mania got you guys. I'm sure it did to us. Every single person in NVIDIA has an agent to himself or herself. And our general purpose of a workday has dramatically changed from the world of Claude Code to the world of OpenClaw to your own personal AI agent acting by your side, autonomously executing long-running tasks much after you've left the workplace is just fundamentally game-changing. So with that and recognizing OpenClaw's popularity, NVIDIA announced the NemoClaw reference OpenClaw. And simply put, the two takeaways here are OpenShell and NemoClaw, separate and aside from what you saw with respect to OpenClaw. And so what OpenShell does is it serves as a runtime, a secure runtime for AI agents, so where agents can operate. It has built-in guardrails, policy controls, system-level permissions to ensure that it's game-changing and ready from an enterprise perspective. Your actions are governed, it's observable, it's compliant with enterprise policies. That's what OpenShell gets you over and above what OpenClaw is. And then NemoClaw is the open source reference stack that lets you run OpenClaw always on AI assistant in a single command. NemoClaw will simply install the OpenShell sandbox and runtime, loads all the supported models. Nemotron is an example of an NVIDIA models. Think of it as a family of large language models, if you want to think about it, and you look at the right. It allows you to safely interact with tools and data and APIs, and it's giving developers a game-changing experience and do so in a secure manner. And so in the world of how we play with NemoClaw, we end up actually installing this on a sandbox, hopefully remote and away from your personal machine, and we talk to it using a WhatsApp or a Telegram messenger. It can leverage some multiple coding agents underneath. It could leverage Cursor, Codex, Claude Code. It doesn't matter. But now I can do so in a secure manner and not worry about some of the policies that I need to. And this is generating tokens like no tomorrow that you possibly don't even imagine. And it's becoming a muscle memory, and the world of interacting with long-running agents is simply game-changing. So again, this is about physical AI and robotics. So to get us back into the rhythm, given those big announcements, it'll be a remiss to not talk about those agents and NemoClaw and OpenClaw. Coming back to physical AI, we think about two approaches to apply physical AI to facilities. One is called inside-out AI, and the other is called outside-in AI. Inside out is the concept of having sensory capabilities, vision-based capabilities for AMRs and robots that move around inside facilities. But as they move around, they're looking out into the environment. That's inside out. And in that concept, we have Omniverse, which is a digital twin framework, and Cosmos, which is a World Foundation family that's grounded in physics. Those fit in the inside out category. And talking about outside in to the right-hand side, these are our infrastructure robots. If you remember, we take large closed facilities, take camera infrastructure in there, literally turn it into a robot, because I'm monitoring through those AI perception-enabled cameras other objects, other robots, other AMRs that are moving inside the facility. And that's why it's called outside in. And we are able to deploy vision-based agents into these infrastructure robots using an NVIDIA blueprint called video search and summarization, and leverages a vision language model underneath called Cosmos Reason. And all that magic comes through what's called NVIDIA Metropolis. So in physical AI, Omniverse, Cosmos, World Foundation models, and Metropolis encompass this world of inside out and outside in AI, clearly where robots are able to operate in both environments. Make sense? Okay, so what is the three computer problem with respect to physical AI? We need three computers for physical AI: a computer to do training, a computer to do simulation, and a computer to do inference. So, with respect to the world foundation models, which are super important for physical AI, they're not your regular large language models. These are models that are grounded in physics, Cosmos Reason, Cosmos Transfer, Cosmos Predict. These models, as well as our robot foundation models called GROOT, Generalist Robot Object Technology, they're trained on a Grace Blackwell 300 NVL72 infrastructure. That's our training computer for training these foundation models for physical AI. Moving on to simulation, which is computer 2 or RTX Pro 6000 Blackwell servers end up running simulation jobs of digital twin environments enabled by NVIDIA Omniverse. And you obviously want robots to learn and refine their skills in a simulated environment within a digital twin of the world, within a platform called Isaac, which is part of Omniverse. So, bottom line, you need a second computer to do simulation and a third computer to do inference. So, our supercomputers from the Jetson family, the Jetson IGX Star for industrial environments, the Jetson AGX Star, which is the brain for a humanoid robot. These are edge-based infrastructure that allows to be deployed in factories and robots from an inference lens, and Metropolis-based vision language models, post-trained robots in GROOT run inference on edge-based infrastructure. These three computers are super important to bring physical AI to life. So I'm not implementing two use cases and three use cases. To implement hundreds and thousands of use cases, I need these three computers. And hence I need an AI factory to be able to basically take that encompassed problem of physical AI and bring that to scale, right? And there's another game-changing moment that we're observing here in the world of physical AI, which is for a long time, real data was a big deal. Getting access to real data and data being the most complex challenge to solve for physical AI was a big deal. But we're now seeing real data is no longer a competitive moat. The hardest data to get was the most valuable for the edge cases, the long tail scenarios, the real world complexity. And it's not the case anymore because compute is data. In the sense, before compute used to process all the data that we used to have, today I'm using compute. I'm taking in real data, I'm post-training some of these models, but I'm using and leveraging compute to generate post-training data over and above real data. So that's the additional synthetic data. And I'm using that to post-train my models. I'm using techniques like classic simulation, neural simulation, reinforcement learning. So compute is data. Like compute's not just processing data, compute equates to data, and therefore real data is no longer a competitive moat. That is a big game-changing observation that you should take note for physical AI. Another big announcement we made at GTC San Jose is the Physical AI Data Factory Blueprint, which is perfect when we are talking about data in that context. This is our unified architecture for data curation, augmentation, and evaluation at scale. I know there's a lot of details in that workflow that you see, but simply put, you have an ability to acquire data and generate data, and you have an ability to curate those data using our curation models. You're able to augment curated data with additional data sets using our models called Cosmos Transfer. And once that data is augmented, I have an evaluation process with Cosmos Evaluator to evaluate and to grade the quality of this data. And at the end, I have an augmented and graded data set. This is happening because of our expertise in autonomous vehicles and robotics over years and years of research over Metropolis development to come up with this beautiful blueprint for Physical AI Data Factory. You finally have something to help generate, curate, evaluate, augment, and you have a data set that's ready to go that you can download and post-train your models and apply Physical AI to life. And to orchestrate all this, you have what's called Osmo, which is at the bottom that you see there. And this is a game-changing blueprint that we announced, and I wanted to share that with you guys from GTC. We spoke about Omniverse, Inside Out. You guys remember a few slides ago? So that's our Inside Out AI. Omniverse is our simulation environment. So think of it as a collection of disaggregated set of APIs and microservices and a digital twin framework that we're providing to developers so that they can integrate it into their physics-based tools or design tools, from Ansys to Cadence to Synopsys to Siemens to Dassault to you name it. All of these engineering tools are taking our Omniverse APIs and libraries and infusing them so that their solvers, their physics-based capabilities can run 10x, 50x, 100x faster than where they need to. Plus, I'm using it as a simulation environment. I can enable RTX rendering to do real-time sensor simulation. And the biggest magic of being able to visualize these assets in 3D with Omniverse is something called OpenUSD. It stands for Universal Scene Description. I can take in disparate data sets from multiple sources and visualize it in real time in 3D. And we bring in a set of blueprints under the Omniverse umbrella and a set of libraries to go do that. And this is a game-changing framework because of which you're able to simulate things virtually before you deploy a large physical change. Robots learn in this environment. They get simulated and they get learned in terms of policies. You can facilitate a brownfield change inside the Omniverse environment. And everything from factory layout and planning. Imagine you're laying out a greenfield factory and you needed to simulate where to place my machines. What's the right placement for these parts to sort of move from one station to the other? What's the way to do some process simulation? What about remote monitoring when it comes to connecting the digital twin to live IoT data from the real factory to doing industrial inspection? How about using AI to check for defects? And how about I need to simulate a fleet of robots inside of a factory which has multiple cameras, but it's not like one robot or two robots. And notice that top right picture, you're seeing multiple robots trying to learn in different environments with friction and inertia and physics. And that's our simulation environment called Isaac Sim. But I can do that within Omniverse, right? And that's the best part about this, which has been game changing. This doesn't replace other engineering tools. The goal of this is to visualize and in a digital twin environment so you can deploy physical related changes and test it before you effect a change. And that is big deal. So that's Omniverse. And moving on to Metropolis, remember the outside in infrastructure is a robot. Metropolis is an AI application. It's a vision AI application framework. AI-powered vision is reshaping how cities and factories and industries and operate at scale. 4 million downloads, 1,500 companies downloading Metropolis. Think of it as a framework and a recipe that helps you talk about how to post-train computer vision models, vision language models, blueprints like VSS, video search and summarization, so that cities can optimize traffic and safety. Factories can improve them reliably, and quality is becoming a paramount piece of topic. Logistics, increasing efficiency. Public spaces are more safer with surveillance. All of the AI perception that I can get through cameras and driving intelligence is what Metropolis brings in. And this is a game changer we're seeing with respect to computer vision enabled capabilities, especially in factory type environments to do quality inspection, anomaly detection, standard operating procedure, and so on and so forth. So I'm going to hit play and show you an example of multiple vision-based agents inside of Metropolis that brings these use cases to life. And as it plays, I'm going to walk through some of these scenarios. You're seeing a safety agent observing an worker tied to an anemometer of a wind turbine, and it's doing a safety analysis to say, is he safely tied or to a harness? And it says, yes, that's the case. This is a warehouse safety agent observing the condition of the aisles as the autonomous forklift is moving across, and it says all the aisles are clear. This is a workplace safety agent, and the cameras are observing workers walking around with or without protective equipment. In this case, he's not wearing a helmet, and it immediately generates an alert. And it's not just about observing these events, they are grounded in space. Look at this scenario where I'm asking BSS on a vision agent, what's the best place to place the large box on the floor? It recognizes spatial characteristics to place the box on the top left. So it's grounded in physics, it understands space, it's grounded temporally in time. And this is an example of an inspection agent, and I'm observing defects in a wafer or a cluster, semiconductor wafer. And in this case, the defects are normal because they were scattered. In this case, it's not, because it's not scattered and clustered in the center. This is an example of an anomaly agent. You're observing using cameras over 15 steps. and one of the critical steps gets missed, and immediately Vision Agent generates an alert because of the vision language model capabilities. Keep in mind, these are not computer vision models. Vision language models are different from computer vision models in that they are contextually aware. They can reason. You can ask what is going on in a video scene and when what happened with respect to time. And the most important is why. Why as in reasoning. Why did such a spill happen? Or why did the warehouse aisle or a factory aisle get blocked? Imagine reasoning through those long tail scenarios. You can't do that with computer vision. It's a 1 or a 0 problem with respect to segmentation or classification. That's the power of vision language models. And we bring this to life with a blueprint called video search and summarization. And we announced VSS 3.0 at GTC San Jose. Simply put, think of VSS as a blueprint that helps you ingest live camera streams, archived camera streams. You ingest that into a vision-based blueprint. The VLM processes that and summarizes the video at 60x speed up compared to the length of the input video. I can do deep agentic search, ask something in natural language, literally, and it decomposes the queries and breaks down the problem and fetches video segments from what's going on in the scenes. I can do contextual alerts and verified alerts, and this is a game changer blueprint. We are seeing massive adoption of vision-based agents with this VSS blueprint because VLMs have changed the game than traditional computer vision, and they run on our target GPUs. So we spoke about vision agents and robots, but to not talk about safety within robots would be a remiss. And so what are we doing with respect to instituting physical AI safety? We announced a blueprint called HALOS, which stands for outside in safety. And simply put, the idea is the following. So you have robot sensors, which have sensory capabilities, and they're moving around, looking out into things. You have AI perception cameras inside of factories looking into some of these forklifts and robots. And how about these two talk to each other to institute safety? If you see that picture on the right, I have an autonomous forklift coming out of a trailer, and I'm turning safety on or off depending on contact with the human within that boundary box or the environment. As soon as he steps in, the forklift stops and it turns the safety on. And as soon as he steps out, it's clear, it drives the efficiency and speeds up that autonomous forklift. Imagine if camera capabilities failed on that AMR. It can't see through occlusions and walls. The reason this is happening is because of outside in cameras and this outside in safety that we're bringing to industrial environments. Again, a game changer blueprint when it comes to instituting safety. Robots are going through this 3 motion of specialist robots, limited scope, deep proficiency. Generalist robots can do a lot of things, but I'm not an expert in anything. But the biggest and most complex trend is generalist specialist robots, robots that have broad scope and deep proficiency. And to bring that to life, you need a workflow that basically takes internet scale data. You take pre-trained models, and you have these post-training data, and you have environments like Isaac Sim to simulate the robots, Isaac Lab for training robot policies, and physics engines like Newton, and our world foundation models like Cosmos. And you post-train some of these robots in something called Groot, which is our foundation model. Groot N 1.7 was announced in early access, used to be 1.6. Groot N2 is coming on the way, and the goal for it is to become generalist specialist robots, and that's coming on the way. So Isaac, our robot platform underneath Omniverse, has Isaac Sim to simulate, Isaac Lab to train policies, Newton, which is a physics engine that we bring to the table, Isaac Lab Arena to kind of evaluate some of the policies of these robots. And a goal is to make them into generalist specialists. So with that, where do I start? We spoke about robotics. We spoke about vision agents. We spoke about Omniverse with respect to digital twin simulation. We spoke about simulating a fleet of robots along with humans. We spoke about robot safety. And all of that is important. But where do I start? Like I could start, today with this notion of creating a digital twin of a physical facility. I could simulate what if scenarios inside a twin. I could deploy vision agents to solve quality problems, defect detection problems, anomaly problems in industrial environments, and slowly add robots into the environment, into the mix such that I can have this poster child on the top right where I can have a fleet of robots working safely along with humans with camera perception and safety and a simulated type environment, and that factories are turning autonomous 24/7 with zero intervention of humans. That's the world we are heading to. And we are solving this next 10-year problem now, and we're super excited about it. That ends my keynote. Again, super excited, and thanks for this wonderful opportunity to Angelbeat. And have an awesome event. There should be other exciting talks, and you should listen to. And happy physical AI, guys.